We had a look at differentiation. Let's go back the other way. At this stage, we're not going to integrate inverse trig as such, but our answers will be inverse trig. In extension 2, we'll see how we can handle the inverse trig. So remember what we saw yesterday. We integrated inverse sine, and we ended up with something like this. So if I've got dx on the square root of a squared minus x squared, it must have come from inverse sine x on a. But of course now we have an alternative, because the only difference between inverse sine and inverse cos was the negative sign. So we could write it as minus the inverse cos of x on a. Which one to use? Well, it doesn't really matter, they're both correct. However, later when we look at simple harmonic motion, then it'll become important which one we choose, just to make the question easier. So, but that's still to come. And tan's the one we've got to be careful with, because remember it had a on the top as well. So for this one we'll get 1 on a, the inverse tan of x on a. Well, again, to generalise it, what are we looking for? Remember that idea of derivative? If we see it and we can create derivative on the square root of a squared minus function x squared, you'll actually get function x on a. Notice, instead of writing 1 minus function x squared, I put a squared there, because then that will save a bit of work there. We can think of it as function x on a. A lot of times that will be 1 anyway. Or, of course, negative the inverse cos. And inverse tan, again, we're going to have the 1 on a out the front with that one. Let's do some. So we have dx on the square root of 4 minus x squared. It's in the form a squared minus x squared. So I can go, well, inverse sine x on 2. Dx on 9 plus x squared, in the form a squared plus x squared. But remember, inverse tan 1 on a, inverse tan x on 3. Here's a definite integral. Again, it's in the form a squared minus x squared. So we get inverse sine of x on root 2. You're going to see that sort of thing a lot, because when we sub in, we get an exact value. You know, the 1 on root 2, root 3's on 2, that sort of thing. So we'll get inverse sine of 1 on root 2, which is pi on 4. Remember, it has to be radians, minus inverse sine of 0. So pi on 4 minus 0, pi on 4. Find the derivative, hence evaluate. Well, I'm kind of expecting that my derivative is going to look something like that answer in the integral. Otherwise, what's the point of the question, really? So, derivative of inverse sine, it really feels like I'm going to cheat here, because honestly, I would just look at that and go, oh, well, it's the derivative, and all I've done is written down what's in that integral sign. But I honestly didn't just write that down. The derivative on the square root of 1 minus the function squared. Hence evaluate, well, therefore, when I integrate that, I must get the inverse sine of e to the x. Still have to substitute in, of course. We're going from minus log 2 to 0. Okay, sub in the 0, that's okay, because e to the power of 0 is, of course, 1. Got to play around with the e to the minus log 2. E to log will cancel, but e to the minus log won't. So I've got to get that minus sign into the log. So that becomes log of 2 to the power of negative 1, which is a half. But now the e to the log will cancel, and we get inverse sine of a half. Inverse sine of 1, pi on 2. Inverse sine of a half, pi on 6. We end up with pi on 3. Dx on the square root of 4 minus 9x squared. Okay, I want to create what on the top? The derivative. The function, remember, it's the function squared. So it's not the derivative of 9x squared I'm looking for, it's the derivative of 3x I'm looking for, because it's the function squared. So 3 will go on the top, a third will go out the front. And now I have it in that form, so I can now say a third inverse sine function x on a, so it's over 2. So 12b will play with the integration.